Hello and good day everyone. So today we will discuss about the column analysis and design. So this will be the last topic under the AB principle for AB structure design. Okay, so let's start. So let me have this first introduction. So columns are usually considered as vertical structural elements, but they can be positioned in any orientation. So usually, ang nakikita nato nga column is constructed nga vertical gid siya. So dili siya limited pa na. So there are also some columns that are constructed in diagonal, just like what we see in a truss. So diagonal siya ang position. So it's also a column. So column supports compressive loads from roofs, floors, and bridge decks. Then columns transmit the vertical forces to the foundation into the subsoil. So it's the main job of the what do you call that? The column, to transmit all the forces from structural members constructed at the top of it, so that it will transmit its load to the foundation of the structure, to the foundation of the structures. Okay, so the work of the column is simpler than the work of a beam. So the loads applied to a column are only axial loads. So unlike sa beam na natay load nga sometimes na couple, na ay transverse loads, also nara po siya axial. So sa column, isa lang yun ang load nga ma-apply. So nanatay axial loads. When we say axial loads, it's parallel to the longitudinal axis of the structures. So loads on columns are typically applied at the ends of the member, producing axial compressive stress. However, on occasion, the loads acting on a column can include axial force, transverse loads, and bending moments. So example is a beam columns. But we will not discuss a beam columns. We will only focus on a column alone. Okay. So columns are defined by the length between supports, and so we have two classification of it. So we have the short columns and long columns. So we will discuss what's the difference of this later on. So just remember, there are two types of column. So short and long. So columns are major structural components that significantly affect the building's overall performance and stability. Columns are designed with larger safety factor than other structural components. Then failure of a joist or beam may be localized and may not be severely affect the building's integrity. For example, there is a redundancy with girders and beams, but not with columns. So it is the most important structural members because all the loads are being transferred or gi-carry niya tanan. So gikan sa roof to floor, gi-carry niya ang load. So karon, if you observe, nga mo nang taas ang atong safety factor it is because once the column fail, the whole structure fails. Ato siya i-observe ninyo, if the column fails, murag ang tanan ang overall structure gyud is maguba. Pero kung ang roof, let's say for a roof, hintay nagguba ang truss. So ang truss lang gyud guba. So dili siya no. So mo na ang pinaka-important gyud, isa gyud siya sa pinaka-important isang column kay once ang column is ma-fail gyud ang overall structure. So ma-observe na ninyo no sa kanang mga kung sakali sa balay, kung maguba ang gyud yung column, siyempre mahugmak gyud ang balay. So importante na ang column. That's why we provide a larger safety factor for it. Then column slenderness and length greatly influence the column's ability to carry load. So mo gina siya ang duha ka factor nga ato i-consider pag kuwanta column, ang slenderness niya ug ang length. So muna nga natay duha ka classification of column, natay short, natay long. So slenderness and length. So very short column can be failed by crashing due to material failure. So kung bubo ra kay siya, bubo lang kay nang imong column, ang possible failures nga mo-occur is due to crashing. So failure occurs once the stress exceeds the elastic limit of the material. You know that kabalo naman noon sa ang yield point, if we will go back to the stress and strain diagram, kita nyo dito asa dapit ang yield point or the elastic region niya. So if mo exceed diha na if short column siya, then natay failure due to crashing. So for short lang na siya. Then for long, which is mostly pag long siya slender, so slender column fails by buckling. So a function of the column's dimension and its modulus of elasticity. So pag taas ka ang imong column, mapo ni ang failure. Mala nyo remember, pag short, possible failure is due to crashing. Pag long, due to buckling. So what is this buckling? So buckling is the sudden uncontrolled lateral displacement of a column, at which point no additional loads can be supported. So failure occurs at a lower stress level than the column's material length due to buckling. So so for example, if you have this column here, it is constructed in a vertical position. So buckling is the sudden change in lateral movement. So if they have this vertical here, na kay murag curve. Kung kabali pa kung ato siyang i-relate nato siya into deflection, but in a lateral position. So if na kay mo bawog diri siya dapit sa vertical niya position, so that's buckling. So most of the long column, mapo siya failure. Okay? Kung mas taas ang imong column, dili siya ma-crash. Kung taas imong load, iba taas ang imong compressive load, dili siya ma-crash, but instead, mo buckle siya. Okay, mo nang mabawog ng imong column. So for short column, dili siya mo buckle, ma-crash siya. Okay, kung taas ang compressive force, nag-i-apply karon, instead of mo buckle siya, kaya gamay mo ng iyang length niya, iyang effective span. Instead of buckling, mo nang ma-crash siya. So that's the difference between the two. So in designing, you will consider this two, the crashing failure and the buckling failure. So this is the summary of the difference between the short column and long column. So other books are using a different let's say for this length dimension, other books are utilizing a different numerical value for this, especially for this slenderness ratio. So slenderness ratio, magdepende siya sa formula na gamit. So we have Winslow, we have the force product. Then, okay, so ano siya? Basta, remember that by crashing, then long column will fail to buckling. So ano siya pinaka number one ko ang get difference between sa duha ka type of columns. Let's start with short columns. So short column fails by crashing at very high stress levels that are above the elastic limit of the column material. So compressive stress for short columns based on the basic stress equation. So remember that stress can be calculated by force over area. Okay, that this FA here stress, where this P is the actual and A is area, it must be less than or equal to FA. This capital FA here is the allowable bending, allowable compressive stress. So you will just remember if this value here, a small f, will exceed this value, then your structure will fail. So always very basic na ito, ginakapila na ito, ginabalik-balik siya. Always yun na dapat lesser ang imong value sa imong allowable compressive stress. Okay. So here, the actual compressive stress, we have the cross-sectional, the actual load, then the allowable compressive stress. Okay, so that's not lang simple ang short column. So basic nga formula for stress. So long columns. So long column fails by buckling at stress levels that are below the elastic limit of the column material. So very short column lengths require extremely large loads to cause the member. So if you want mabuckle ang very short column, you need extremely large loads. But instead of mabuckle, large load, it presents high stress that causes crashing rather than buckling. So may tabo. Pero pag may tabo sa long columns, then it will buckle. So buckling in long columns due to the following. So first is the eccentricities in loading, then irregularities in the column material. So although irregularities in the column material, no, kay naman tayo mga column na ginagamit nato is reinforced concrete. So we have steel bars, then a concrete. But it's different analysis na po natong isubayan. This time, we will only focus on a homogeneous material, so steel and timber. But I will only discuss the timber column. I already upload the steel, but it's just for your advanced reading na lang po, no? Additional information about steel column. But I will only include in the exam about timber column. So buckling can be avoided if the loads were applied absolutely axially. The column's materials was totally homogeneous with no imperfection, and construction was true and planned. So mo siya but it is possible to permanente natin na siya ma-take account because we're dili man siya perfect yet. So okay, so again, focus na to karon is ang long column. So I know that long column will failure niya is backlinking. A Swiss mathematician named Leonhard Euler was the first to investigate the backlink behavior of the slender columns within the elastic limit of the column material. So Euler equation shows the relationship between the load that causes buckling of a pin and column and the material of stiffness and properties. So mo siya si Euler, mo na natay Euler formula for backling. So the critical backling load can be determined by the following equation. So this is the one derived by Euler. So this is the calculate the critical load. So it's quite simple to remember. Just pi squared EI over L squared. So your equation is valid only for long, slender column that fails due to backling. So if your column is short, do not use Euler formula because Euler formula will be used only for long columns. So Euler equation contains no safety factors. Euler equation results in compressive stresses developed in columns that are well below the elastic limit of the material. So remember. Okay, so let's slenderness ratio. So again, the property of the best property to determine sa unsa kanindot ang atong column is gamit ang slenderness niya o ang length. So slenderness ratio, so it's one of the property of a column. So this formula here is used to calculate the radius of gradation. I think you're familiar with the radius of gradation because it's I think in dynamics. Okay, so we have here this formula. So just derive the formula for radius of gradation. So using that formula, we will substitute that. So we know that the stress is just P over A, or the force over A. So, but we will include the critical coordinate. So this is the Euler formula. So we will use the P critical. So just substitute the P critical, and then we know that I, the moment of inertia, as presented a while ago, is just equal to AR squared. So by simple manipulation, we can calculate that the critical stress for a long column can be calculated using this equation, which is pi squared E over L, the quantity of L over R squared. Now, this is now the modified equation for calculating the critical stress, the compressive stress for a long column. Okay, notice this equation class, this L over R. This L over R is what we call the slenderness ratio. So, imply the higher slenderness ratio means a lower critical stress that will cause buckling. Remember, higher ratio means lower critical stress that will cause buckling. Conversely, lower slenderness ratio result in a higher critical stress, but still within the elastic range of the material. That's why in calculating the LR, sometimes we calculate two 2 LR for one column lang. So duha to with respect to y and with respect to x. So we will see if what will happen if kuan duha atong kuan. So atong i-take atong tanawon karon kung unsa ang dako nga value. So mo to siya ang kuan. So kung unsa ang dako nga value mo to siya atong gamiton for slenderness ratio for our formula here. Okay. Just remember na lang atong mga formula. We will balikan nato to niya. Okay, so now let's proceed to axially loaded columns. Simple solid columns consist of a single piece of wood, square, or rectangular cross-section. Okay, so we will only, this time we will focus on timber column. For steel column, I uploaded the material for it. You can read that, you just study that, because I will not include that in my exam, but please do study sa katawan. The process in solving sa steel and timber is quite the same, but focus lang kita sa kaning sa timber columns. Okay, so this is the design formula. Ano siya na basi nalibog mo karon, sir, anong row no, sir? So this row here is pwede na to siya i-substitute itong f nga gamay kanina, fa, then this part here will be the katong capital F. So it's just the same. So the other books are using different variables. So I utilize different books. Okay, so but it's all it's the same. It's this is the actor, this is the allowable. This P is the actual load. So how to calculate the slenderness ratio of timber? In wood columns, the slenderness ratio is defined as the laterally unsupported length in inches divided by the least dimension of the column. So slenderness ratio can be calculated by L over D. Ganina, the slenderness ratio is L over R, where R is the radius of gradation. Karon for timber, we will use this formula if our cross-section here is rectangular or square. So L over D min. So D min is the or D1 or the minimum or the least dimension. Okay, but there are some cases if your column is supported laterally. If your column is supported laterally, you will calculate 2 again, as I mentioned kanina. Makakalculate og duha ka slenderness ratio with respect to y and respect to x. So I will show you an example for that later on. So just remember that slenderness ratio is L over D1. So here, it's the length divided by the least dimension. So we have different formula for calculating the modified stress, compressive stress for a column. So, but we need to classify first if your column is short or long. So how to classify it is through the use of your slenderness ratio. So first is you need to calculate less than 50. You can say that it is long column if it is Winslow formula. So Winslow 15 and 50. So you calculated the L over D, it's greater than 15, let's say 20, but less than 15, then it's long column. You can calculate using this formula here, that this FP is the allowable bending stress of your column. If your slenderness ratio is less than 15, then you can say that it is short column. Then you can calculate this. You can calculate the modified, what do you call that? Modified stress, compressive stress using this formula. F is just equal to 3/4 FP. So just simple as that. If we're using Winslow formula, but most of the time, problems are giving modulo function with modulus of elasticity. So we will use the force product formula with that. So for again, calculate the slenderness ratio. If the slenderness ratio is less than 11, then you can say that it is short column. Then you will use this formula la katong basic nga formula that force over A is just equal to the compressive stress. So it is equal. But if your slenderness ratio is greater than 11 but less than K, which is K is the length factor, then we have another type of column here, which is the intermediate column. How to determine this value of K? You will use this formula here, that K is just equal to pi over 2, the square root of E over 6 FP. Or this is the reduced formula, K is just equal to 0.641 square root of E over 6P. I think, I'm not sure, wala na ng 6, wala na siyang 6. Right. Wala na siyang 6 ha. It's only na lang. Now, if you calculate that K will satisfy this, then you will use this formula here, that the modified allowable compressive stress or the reduced allowable stress can be calculated using this formula, that Fp is multiplied by the quantity of 1 minus 1/3 multiplied by the quantity of L over Kd raised to the power of 4. So you will use the formula if it is intermediate. Now, if it is long, if your slenderness ratio is greater than K, but less than or equal to 50, then you can say that your column is a long column. Then you can calculate the modified allowable stress using this formula, pi squared over E, 36 over L over D, where L over D is just the slenderness ratio. As you observed last, this formula here is mo itong gigamit ni Euler. Diba? Itong reduce na ito formula, but there's all 36. I think it's for, depende sa unit na gigamit. But you can use this formula, pi squared multiplied by E over 36 L over D squared. So you will use this formula for columns that is long. If you will satisfy this equation here, that K is less than to LD, but LD is less than or equal to 50. So sometimes we design a column that is round. So if it is round, you can use this design. Long or not, you will use for long columns that are round lang siya. So this D here, dili na ni siya ang radius, dili na ni siya ang katong least diameter. So this is not the equivalent. D is the equivalent square section. So how to calculate this D? You will use this formula in which D, the capital D, is the diameter of the round column. So ang ibuhatan is we convert the diameter of the round column into the equivalent square cross section. So it's just the radius of migration if you will use the R. Okay. So I think we're done with discussion. So we will proceed now to an example. So first example. So a 12 centimeter by 15 centimeter triangular column with an unbraced length of 5 meters is used to carry axial load P. The allowable compressive stress parallel to grain and modulus of elasticity are 11.70 MPa and 13.8 gigapascal, respectively. So find the column classification, the modified allowable stress, and the maximum load P column that can support this. Okay, so first is the classification. So how to classify columns. So since gihatag karon ang modulus of elasticity, then we will use the force product formula. So how to classify it? Using the slenderness ratio. So the slenderness ratio is L over D. So we have the length L divided by the least na itong dimension, which is 12 centimeter. Then we can calculate that the slenderness ratio is 41.67. So 41.67 is greater than 11. So therefore, it is not as short. So it can be intermediate or long. So we need to check for K. So for K, we need to calculate using sa E and FP, we calculated that K is just equal to 22.01. So it will satisfy this equation here that 11 is greater than SR, but no, not K, not 11. It is K. K. Sorry, it's K. Not 11, it's K. So K is less than to SR, then SR is less than or equal to 50. Therefore, we can say that the problem, the column, the type of column given by this problem is a long column because it will fall under the criteria for a long column. So if it is long column, then we will use the modified to calculate the modified allowable stress. So using this formula, so F is just equal to P over A is just equal to pi squared E over 36 multiplied by slenderness ratio squared. So by just simple substitution, we have the value of E, then this is the reduced, the reduced, reduce. So we have, what do you call that? Value of slenderness ratio. Then we can calculate that F is just equal to, or the modified allowable stress is just equal to 2.22 MPa. So this is now the modified. So this is based on the actual, base of the actual load given by that problem. So we have that actual load. I-calculate pa natin ang actual load. So this is based sa katong load. So, but we need to calculate the actual load using some basic formula for stress, which is P is just equal to FA, or F is just equal to P over A. So just use this F. Then we have this cross section here, 12 and 15. Then we can calculate that the maximum allowable load, or the actual load present in that structure, is 39.96 kPa. Okay, so if you have question about basin na ako'y na mali sa pag-calculate dire, you can just ask me basin na sa'yo. But the process is inanigid process. So first is you need to identify na siya ka-simple. First is you need to identify what type of column. Then after that, you calculate the modified allowable. Then calculate the maximum load for that problem. So there are also many other problems that you need to design. So what would be the size? So if what would be the size? Then it's a function of the area. So you need to use that just manipulate the equation so that you can but the equation will revolve katulad dito. Okay, so I think I have another example here. So a timber column, 7 meter long, and it's laterally supported at 0.3 meter from the bottom, carries an axial load of 240. If the allowable compressive stress parallel to the grain is 10.34 MPa and the modulus of elasticity is 13.8 gigapascal, design the column section. Okay, here, so we need to design. So we have here now, we have a column. Ang length sa itong column is 7 meter. Mali ang pag-note na ako sa distance. But it's the total length of this column is 7 meter. But we have the lateral support at 3 meters from the ground. So right here, no? Right here. So we need to design what would be the size of this column. Natay support, remember that we have a support here. We have a support here at 3 meter. Okay, so again, first thing to do is to calculate the slenderness ratio. But ano na nga tong least distance? So our equation for SR will be L over D equals 4 over D, which is ang 4 is the span of the, remember that 4 meter is the span of the unsupported. Okay? Unsupported, katong sa top. So we have the 3 meter is supported ang 3 meter. Relative to y-axis na siya. Kung atong tanawon sa relative to y-axis siya, supported ang atong 4. So therefore, ang atong unsupported span niya is 4 meter. So that's why we use 4. So we need to calculate man sa design. So we need to assume. So at first, 2,000 at 240,000. Then we have the allowable stress na 10.34 MPa. So we need to calculate the area. So we have area of 0.0232 meters squared. First, let's assume that a square cross-section. So therefore, if it is a square cross-section atong column, therefore B is just equal to D. Then the area can be calculated by B times D. But if it is equal, we can modify the formula equals to A equals to B squared. Then using this value for area, we can calculate that the B is just equal to 0.152 meter. So let's say, let's adjust this for safety purposes. Let's adjust. Let's say 200. So therefore, our dimension for B is 200. So since it's square, then D is also square cross section. Okay, so we have now the first value for dimension. So we have the value of B and D is just equal to 200. Okay, now we need to calculate 2SR. Why? Because relative to y-axis, ang unsupported niya is only 4 meter. Kato nga, balik class. Kung mo na yung mong class, mo na yung mong beam, gi-support siya dere. So, ang tanaw na to, ang unsupported lang is kani. Pero, if we will look side view, side view ha, instead ka cross, instead ka nag-cross mo ito nga na, instead ka cross, ato siyang tuyok, maginaya na siya. So, therefore, ang unsupported length niya karon is ang total length. Wala na support relative to that axis. Di ba? Kaya ang support niya is within that axis lang man. Pero i-rotate na to siya, we will look at this part here. Kung nag-ana ng imong support, then dili siya, ang total length niya, unsupported span, is 7. But ang iyang dimension, less dimension na is wala nang change. Di ba? Wala nang change. Ang iyarga akong dimension karon is only 0.2 hapon. So we need to calculate again. Atong purpose ani is to calculate the greatest LR. Not LR, SR. Again, kay atong gi-mention na no, mas dako ang SR, mas nindot siya. Okay? So we need to calculate SR. So we calculated that the greatest SR for that is 35. So point-to-point lang atong gigamit since D1 is 0.2, then D2 is also 0.2. But if D2 is, let's say, lahi siyang value, let's say 150, then you will use 150 because it's relative to that axis naman. Okay? So let's use this 35 here. So let's check first if this 35 here can be, masay tawag na ito, makaingon ba tayo long man siya or intermediate ba? Then we will use the value for K. So value for K, calculate that value of K. So K is 23.51 using this equation here. Okay. So K is less than with SR, but SR is less than or equal to, less than to 50. So therefore, we can say that our column is a long column. Okay? So it's a long column. So therefore, we can use this formula here. But if we will calculate here, we can calculate the modified allowable stress. But instead of calculating the modified stress, let's check if this dimension here is satisfied to the actual load, which is 2,400. Okay, so we will use what value of P that could, you calculate this value. You can calculate that a certain value for allowable stress. So that's stress. But ang atong purpose karon is with that allowable stress, pila ang load. Ang possibility magod, if basin dahil katong allowable stress, ma-reach to siya, moro katong modified, pero ma-reach to siya lower than the 240. Just to make what happen here. No? So, let's say, so atong showed na to, so plug in na to 0.200 to 0.200. So calculate. We know that P is 123,537.91 Newton. So that's the value for P. For that allowable, just imagine, more niya itong modified or more niya itong allowable kaning value diri. If you will calculate this value here, class, mo lang niya ang atong allowable stress. Pero ma-reach ni siyang allowable stress sa kanilang load. Di ba? So 123,000 pa lang, ma-reach niya daan ang allowable. So therefore, fail siya. Not safe siya. Okay, ang atong load man, ang actual load nato is 240,000 na. So therefore, masabdan ninyo. Just imagine, if you will calculate to, please calculate this stress. The value of this is stress. Okay, so with this stress, ma-reach ni siya nga stress using this load. Okay, the dimension is fixed, right? Dimension is fixed. But the load, it will vary. So what if 240 will ma-reach it siya? So therefore, it will fail. No? So therefore, our design is not safe. This 200 na itong square cross-section is not safe. So therefore, we need to redesign. So how to redesign? So let's say, back to the sa itong first gibuhat na no. So again, the same, but this time, we will not assume that it is really siya cross-section. But instead of 200 atong B, which is the same B, neglect this equation na solve. Okay, first nato equation na to is nasa this B equals 200 man. But this equation is not true if we will use this. But let's say na kabalo mata nga ang pwede nga initial nato nga distance for a dimension for B is 200. So let's adjust lang sa isa ka dimension. So we will not use this equation. So let's say 200. So from 200, so i-adjust na ako ang katong D from 200 to 250 na. Okay? So if we will adjust, this is what happened. So first, calculate the SR. So the same for kani. Then for another SR, so we question no, katong ganina, 4 is the unsupported relative to Y, 7 is the unsupported relative to X. So we can calculate that the greatest or the larger SR is 28. Okay, so atong K value na calculate natin kanina, which is 23. So therefore, long column yapon siya, but 28 na ang iyang SR. So again, back to the katong formula for calculating the modified. Let's check for P. So substitute the same process katong kanina class. So we can calculate that the load P is 241.284.97, which is greater than sa katong allowable nato nga 240. Therefore, pasabot niya class that in order to reach this value here, kaning value diri nga stress, you need this amount. You need this amount of load. But ang actual stress na represented is 240, which is less than with this. So therefore, bisang pag mo reach tong 240, your structure will not fail. Gets? I hope that you can answer. No? So that's this value here requires 241. Then the actual load will only the actual load is the maximum actual load is 240. So therefore it's safe, but it's very close with the value. No? So try to design. So I think it's try to practice. So what would be the best? But safe, but not the value is close enough with Kuan. So just so I think you need to. So with that, you can use the 200 mm by 250 cross section. So say mo as a practice is try to solve. So what would be the best? I think so. Makita naman niyo ang trend niya here or maybe here. So you can calculate that. Okay. So I think for the cross-sectional area class, I think ma-change structural what do you call that? Structural kanya. But the thing is, you can you can nag-range gyapon siya no, nagamit gyapon nato ang katong allowable stress, the modified allowable stress, and also the modulus of elasticity. Okay, so I think that's all, no? So thank you for listening for this video. So again, this is the last topic under the what do you call that? AB principle under sa AB structure design. So the next topic will be the design criteria. So I already upload the material for it. You can read that because it's more on reading lang naman. So just read and just wait my announcement for our schedule for our exam. So that's all. So thank you and goodbye.